Organic chemistry. Just hearing those words can send a shiver down your spine, right? It's got this legendary reputation for being one of the absolute hardest subjects you can take, a seemingly endless mountain of reactions and rules to memorize.
And yeah, this quote, it just hits the nail on the head for so many people. It really can feel like you're just moving things around with any rhyme or reason, just hoping you stumble upon the right answer without having a clue why it's the right answer. So that's the big question we're going to tackle. Is it really just a chaotic mass of disconnected facts, or is there an elegant, hidden logic under the surface? Well, what if I told you there is, and that it's actually way simpler than you think?
So, let's crack this code. The key to making sense of all of it, the entire subject, isn't about memorizing hundreds of different reactions. Nope. It's about understanding one single universal driving force.
And that driving force is stability. Seriously, that's it. That is the secret sauce. Every single reaction, every electron that moves, every bond that forms or breaks, it all happens for one reason. Everything in the universe is trying to get to a more stable, lower energy state. It's a constant, relentless quest for calm.
So what do we even mean by stability?
Well, for a molecule, it just means low energy. A stable molecule is a chill molecule. It's not looking to start a fight, so it's not very reactive. Think of electrical charge, like a negative or a positive charge, as a form of molecular stress. The more you pack that stress into one tiny spot, the more unstable that molecule gets. So to find its zen, a molecule has to deal with that stress by either getting rid of the charge or, even better, by spreading it out.
Okay, so if they're all chasing stability, how do they actually do it? Let's start with the first and most straightforward tool in their toolkit. It's something called the inductive effect.
Picture this: a molecular tug-of-war. The rope is the electrons in a chemical bond. Now, in a simple chain of carbon atoms, everyone's pulling with about the same strength. It's a nice, even match. But then you bring in a heavyweight champion, an atom like fluorine. Fluorine is what we call highly electronegative, which is just a fancy way of saying it's an electron bully. It yanks those shared electrons toward itself, creating a little pocket of negative charge on its end, and leaving the atom it's attached to a little bit positive. Now, there are a few ground rules for this tug-of-war. First off, this isn't temporary. As long as that fluorine atom is there, it's pulling. It's a permanent state of affairs. Second, this pull travels through the chain of single bonds. And third, just like a magnet, the pull gets weaker the further away you get. So the carbon right next to the fluorine feels it a ton, the next one feels it a little less, and by the time you're 3 or 4 carbons down the line, the effect is pretty much faded away.
Okay, so pulling electrons to one side is one strategy. Kind of simple, right? But what if there was a smarter way to handle that stress? Instead of just one atom taking on the burden, what if a molecule could share it across the whole team? Well, this brings us to the powerful concept of resonance.
This is where things get really cool. The inductive effect is like one person deciding to shoulder a little more of the weight. But what happens when the entire group can just spread that weight out evenly amongst themselves?
And that is exactly what resonance is all about. So look at step 1. You've got all that stress, that negative charge, stuck or localized on one single atom. That makes it really unstable and ready to react. But then, if the molecule has the right structure, the electrons can move around. We call this delocalization. And the result, in step 3, is what we call a resonance hybrid. That charge is no longer stuck, it's effectively smeared out over multiple atoms. And since nobody has to carry the full load, the whole molecule becomes way, way more stable.
All right, we've gone from pulling charge to sharing charge, but believe it or not, there's one more level. This is the absolute holy grail of stability. It's a special status that brings an almost unbelievable level of calm to a molecule. So let's talk about the VIP club of chemistry, aromaticity.
And the poster child for this incredible stability, the celebrity of the VIP club, is a molecule called benzene. It was first isolated by the brilliant Michael Faraday way back in 1825, and for decades, chemists were just baffled by it. It was so unreactive, so stable, they knew something special was going on. That special something, they eventually figured out, was its aromaticity.
So what is this magic property? Aromaticity is the grand prize. It's an extra special, supercharged level of stability that only applies to certain molecules that are flat and shaped like a ring. What they have is a perfect, continuous, uninterrupted loop of shared electrons. You can think of it as resonance on steroids.
And yeah, you can't just waltz into this club. There's a strict dress code. First, the molecule has to be a flat ring. Second, it needs that continuous loop for the electrons to travel on. And third, and this is the really weird one, it has to have a very specific magic number of shared electrons. For benzene, that number is 6. It's like a secret handshake. If a molecule meets all these criteria, it gets past the velvet rope and is rewarded with just an exceptional level of stability.
Okay, so inductive effect, resonance, and the VIP club of aromaticity. This might all sound a little abstract, like a bunch of theoretical rules, but here is the amazing part. These simple rules perfectly predict how these molecules are actually going to behave in the real world.
So let's put our new theory to the test. Can this whole quest for stability idea actually explain a real, measurable property? Let's take a look at something like acidity. First, a super quick refresher on what acidity is. In chemistry, an acid is just something that's good at donating a proton, a hydrogen ion, or H+. The more easily it gives up that proton, the stronger the acid. But why would a molecule want to do that? You guessed it, it will only willingly give up a proton if the molecule that's left behind is more stable than the one it started with. It all comes back to stability.
And this is where it all clicks into place. This is the aha moment. Take a look at these two molecules. On the surface, cyclopentadiene and cyclopentane look pretty similar, but let's see what happens when each one loses a proton. When cyclopentane loses one, you're left with that localized negative charge. All that stress is stuck in one place. That's unstable. So it really doesn't want to do it, making it a very weak acid. But cyclopentadiene, when it loses a proton, something incredible happens. The molecule that's left behind suddenly checks all the boxes for entry into the VIP club. It becomes aromatic. To get that ultimate prize, that incredible stability, it will gladly kick out a proton. And that's what makes it a surprisingly strong acid. And there it is. What seems like a totally random fact is perfectly explained. Molecules will do almost anything to become aromatic. It is the ultimate trump card in the stability game. So the chaos isn't chaos at all. It's actually a beautiful, elegant system, and it's all governed by that single relentless pursuit. So let's just zoom out for a second and bring this all home. What's the one thing you should really take away from all this?
It's this number, 3. Just 3 core principles that bring order to all that chaos. You've got the simple tug-of-war of the inductive effect, the clever burden sharing of resonance, and the ultimate grand prize of aromaticity.
And look, this is way more than just some academic exercise to help you pass an exam. Understanding this deep-seated drive for stability is how chemists design and build the world around us. It's fundamental to creating new life-saving medicines, developing innovative materials, and even understanding the very biochemistry that makes us tick.
It really makes you wonder, doesn't it? If a subject as famously complex as organic chemistry can be unlocked and understood with just a few elegant underlying principles, what other parts of our world that seem impossibly chaotic are really just hiding a simple logic, waiting for us to find the key?